Welcome. Today, we explore the remarkable legacy of Max Born, the mathematical architect of quantum mechanics. Beyond the matrix formulations and mathematical abstractions that reshaped modern physics lies a profound human story of brilliant insight, forced exile, and quiet resilience. Join us as we uncover how Born constructed the enduring scientific scaffolding that continues to underpin our understanding of the quantum universe. Max Born's journey spans continents and pivotal eras of modern physics. Beginning with his early years in Breslau, his path led to Göttingen, where he revolutionized quantum theory by formulating matrix mechanics and the Born rule. Driven into exile by Nazi Germany in 1933, he found refuge at Cambridge, accepted a brief invitation from C.V. Raman in Bangalore, and ultimately settled in Edinburgh as Tate Professor, co-authoring the landmark Principles of Optics. Across these geographic epochs, Born's intellect transcended borders, leaving an indelible imprint on science amidst a turbulent world. At the University of Göttingen, Max Born was shaped by mathematical titans, Felix Klein, David Hilbert, Hermann Minkowski, and Carl Runge. Guided by their influence, Born bridged pure mathematics with applied physics, using abstract concepts as a lens to decode physical reality. This approach culminated in his first major triumph, his 1906 PhD thesis on the stability of elastica in a plane and space. By mathematically proving the behavior of elastic wires and tapes under tension, Born earned the Philosophy Faculty Prize, establishing his hallmark ability to anchor abstract theory in physical reality. In 1925, Werner Heisenberg captured scattered, perplexing quantum data, struggling with variables that refused to commute. Max Born recognized the underlying order. Heisenberg's raw insights were naturally describing matrix calculus. Working alongside Heisenberg and Pascual Jordan, Born transformed these chaotic data points into a structured matrix framework. This landmark breakthrough yielded matrix mechanics, the very first cohesive mathematical language for quantum theory. In 1926, Max Born shattered classical physics by introducing the Born rule, replacing Newtonian determinism with quantum probability. While classical mechanics promised exact, predictable trajectories, Born reinterpreted Erwin Schrödinger's wave function as a statistical probability density. This conceptual leap proved that the atomic world could only be described through probabilities rather than absolute certainties. It fundamentally redefined physical reality. A radical shift from determinism that giant figures like Albert Einstein, Max Planck, and even Schrödinger himself famously struggled to accept. In 1927, Max Born and J. Robert Oppenheimer delivered a pivotal insight that accomplished far more than solving a mathematical hurdle. By establishing the separation between the structural scaffolding and the atomic swarm, they created the enduring conceptual framework for understanding quantum mechanics. Today, this fundamental blueprint governs how we visualize, calculate, and engineer the material world, forming an indispensable foundation that continues to underpin virtually all of modern science and engineering. Collaborating with J. Robert Oppenheimer, Max Born brought order to molecular chaos through a groundbreaking three-step method. First, they leveraged the vast mass disparity between heavy, sluggish nuclei and nimble electrons. By treating the slow ionic movement as a perturbation, they effectively froze the nuclei to calculate the potential energy surface. This crucial simplification enabled physicists to solve electronic wave functions entirely independently of nuclear motion, turning a complex quantum puzzle into an elegant, practical framework. Solving the exact Schrödinger equation for a molecule is computationally impossible due to the phenomenon of many-body chaos. Every nucleus and electron interacts with every other particle simultaneously, weaving an intractable web of dynamic variables. Take the benzene wall. Modeling a single benzene molecule requires solving an eigenvalue equation with 162 coordinates for its 12 nuclei and 42 electrons. With computational complexity scaling faster than the square of these variables, exact quantum calculations quickly hit an immovable wall. This approximation hinges on a fundamental physical disparity. Protons are roughly 1,836 times heavier than electrons, causing heavy nuclei to move exponentially slower. To a swift electron, the nucleus appears as a fixed, stationary scaffolding. Conversely, to the sluggish nucleus, the hyperactive electrons blur into an instantaneous, averaged electronic fog. By exploiting this vast difference in mass and speed, quantum mechanics separates the static framework from the dynamic swarm, turning an intractable multi-body problem into a beautifully elegant calculation. To break through mathematical gridlock, we clamp the nuclei in place. By setting nuclear kinetic energy to zero, nuclear coordinates transform from dynamic variables into fixed parameters. Stripped of nuclear motion, the system simplifies into the electronic Hamiltonian. Electrons can now determine their quantum states based entirely on an instantaneous, frozen snapshot of nuclear geometry. This crucial step decouples electronic movement from nuclear dynamics, turning an intractable multi-body equation into an elegant, solvable framework. To formalize their physical intuition, Born and Oppenheimer introduced a perturbation parameter based on the mass ratio, kappa approximately equals 0.1. This established a clear mathematical hierarchy. At zeroth order, dominant electronic energy is calculated around stationary nuclei. At second order, nuclear harmonic vibrations enter as oscillations around energy minima. Finally, at fourth order, nuclear rotations and couplings unfold. Because odd powers of kappa vanish, electronic and nuclear motions naturally sever, turning intricate quantum dynamics into a beautifully structured, solvable ladder. Here lies the brilliant stroke of the approximation: the electronic energy eigenvalue doesn't disappear. Instead, it transforms directly into the effective potential field for nuclear motion. In this quantum landscape, electrons shape the topography while heavy nuclei roll through the valleys. Where these valleys hit their lowest minima, stable molecular geometries are born. Governed by this unified framework, the complex dance of subatomic particles is rewritten as a visual, intuitive map of physical matter. The Born-Oppenheimer approximation serves as the bedrock for the dual pillars of modern physics. In quantum chemistry, it maps reactions along potential energy surfaces, powering computational chemistry, transition state theory, and molecular dynamics. In solid-state physics, truncating the perturbation at second order yields the harmonic approximation for vast crystal lattices, unlocking phonon spectra, dispersion relations, and the thermal properties of solids. Together, these pillars bridge fundamental quantum mechanics to the practical engineering of molecules and materials. Yet even this solid architecture has its limits. It fractures when electronic energy states converge. Because the Born-Oppenheimer approximation assumes adiabatic instantaneity, it breaks down near conical intersections where non-adiabatic coupling dominates. Here, nuclear and electronic motions synchronize onto similar timescales, making vibronic coupling impossible to ignore. These quantum funnels drive ultrafast photochemistry and underpin striking real-world phenomena, from the John Teller effect and cone anomalies in graphene to superconductivity. Where the classical scaffolding fails, a richer, fully coupled quantum reality takes over. In 1933, political turmoil shattered Max Born's world when Adolf Hitler rose to power. Suspended from his Göttingen post due to his Jewish ancestry and stripped of his German citizenship, Born was forced to flee his homeland. After a stay in northern Italy, he found refuge at the University of Cambridge as the Stokes lecturer. Amidst this chaotic period of exile, Born tirelessly helped fellow refugees navigate immigration while publishing his highly successful popular science book, The Restless Universe. In 1935, Nobel laureate C.V. Raman invited Max Born to the Indian Institute of Science in Bangalore, hoping to recruit fleeing European Jewish scientists to build a premier physics center. Born delivered over 30 acclaimed lectures, including his famous talk on the mysterious number 137. Yet grand ambition sparked intense academic friction. When Raman proposed a permanent chair for Born, the administration revolted over budget concerns, deriding Born as a rejected renegade. The political clash ultimately cost Raman his directorship. Beyond personal politics arose a fundamental scientific clash, the Raman-Born controversy over crystalline solids. Max Born approached lattice dynamics through theoretical mathematical models from his 1915 Dynamic der Kristallgitter, whereas C.V. Raman relied on experimental optical spectroscopy to challenge Born's theory. Though research in the 1950s and 60s showed Raman was partly right, theoretical physicists overwhelmingly backed Born's mathematical framework, vindicating his approach as mostly right and establishing a lasting pillar for solid-state physics. In 1936, Max Born succeeded Charles G. Darwin as the Tate Professor of Natural Philosophy at the University of Edinburgh, spending 17 years translating complex quantum concepts for students. He authored Atomic Physics, a masterwork that went through 7 editions covering gases, particles, and molecular structure. His 1949 Waynflete lectures yielded Natural Philosophy of Cause and Chance, probing the deep philosophical tension between classical determinism and quantum probability. Through these seminal texts, Born refined physics education and shaped how generations came to understand the quantum realm. During World War II, the U.S. government confiscated and republished Born's 1933 masterwork, Optic, ignoring his protests. When later approached by the U.S. Navy to write a new optics text, a retiring Born partnered with Emil Wolf, a young Czech exile. Over 8 dedicated years, after other collaborators departed, the duo transformed a bitter intellectual property dispute into an enduring masterpiece, creating a completely new foundational text that permanently reshaped modern optical science. When Max Born and Emil Wolf signed with Pergamon Press, they were entangled in a web of subterfuge. Publisher Robert Maxwell operated fraudulent financial ledgers, hiding reprints and claiming poor sales to withhold Born's essential retirement royalties. Driven by professional integrity rather than profit, scientists like Born were particularly vulnerable to such deception. Ultimately, co-author Emil Wolf took Maxwell's company to court and won, triumphantly securing Born's financial legacy. Against Max Born's initial skepticism, Emil Wolf insisted on including in-depth chapters on the statistical properties of light and partial coherence. Published in December 1959, Principles of Optics became an instant classic. When the first laser was invented in 1960, the text provided the exact mathematical framework needed to understand coherent light, seamlessly bridging theoretical physics with the dawn of the laser age. Max Born was physics' ultimate mathematical translator. He structured Heisenberg's raw data into matrix mechanics, turned Schrödinger's wave mechanics into statistical probability densities through the Born rule, and simplified molecular chaos via the Born-Oppenheimer approximation. In optics, his work became the definitive reference for the 1960s laser age. Ultimately, Born's true superpower went far beyond discovery. He constructed the mathematical scaffolding that allowed modern physics to stand. Nearly 3 decades after his breakthrough, Max Born received ultimate validation in 1954 when he was belatedly awarded the Nobel Prize in Physics for his statistical interpretation of the wave function. After spending his retirement in Bad Pyrmont, West Germany, he passed away in Göttingen in 1970. Born leaves behind a humble reflection on scholarship. Crafting a learned work requires not narrow specialization, but simply grasping the core essentials and applying dedicated effort.